We just defined three types of independence. So we had independence of two events, independence of a finite set, or mutual independence of the set of the finite set of events, and conditional independence of two events given another event. And I should tell you that sometimes people refer to independence as statistical independence as opposed to, say, linear independence or algebraic independence or what have you. And let me make a couple remarks here. Or actually, we'll make a couple more definitions. So we can extend the definition for a finite set of events to an infinite sequence. So say we have A1, A2, and so on. And we would say that they are mutually independent. I'll abbreviate by MI. If, and it looks very similar, for any subset S, and now we're considering the index set of this collection, which is 1, 2, 3, 4, 5, etc. If for any S we have, let me say, star, and star is this condition here, it's the same exact condition. Oh, and I should say, this is for any finite subset. Otherwise, this would be a circular definition. So for any finite subset, we have this condition. So for any finite subset, they are mutually independent. Or rather, for any finite subset, the product of the intersection factors. And similarly, we can extend our definition of conditional independence for two events to conditional independence. I'll use the same color here so you can visually match. So we would say that we'll do finite, and you can see how you would extend it, are conditionally independent. I'll abbreviate by CI, given C, if for any S in 1 through n, finite, again, well, in this case it's obvious it's finite because this is a finite set, but we could do the same thing for an infinite set. If for any S subset of these indices, we have the probability of the intersection of the events given C equals the product of the conditional probabilities AI given C. So this is a set of events that are conditionally independent given another event. Now, let me give you a little proposition, a mini theorem regarding conditional independence and independence. So this relates conditional independence to independence. So suppose we have some event B with positive probability. And by the way, I should say here, I'm assuming in these definitions that C has positive probability. I should stipulate that, but in the definition, maybe let me go back and write that. So we also need probability of C is positive here and here in order for these conditional probabilities to be well defined. So back to our proposition, suppose probability of B is 0. Then A and B are independent if and only if the probability of A given B equals the probability of A. So the probability of A does not change when we condition on B. So if and only if, that is, this implies this, and this implies this. So let's give a little proof. So first we'll prove this implication. We have two implications we have to prove. So if A and B are independent, then we have the probability of the intersection equals the product of the probabilities. And that implies we write out what this conditional probability is. A given B equals the ratio, this factors by applying this. So we get PA, PB over PB. They cancel, and we get the probability of A. So that implies the right side. And we can do the converse. So we're supposing this and this implies, so what do we need to prove? We need to prove these are independent. Actually, let me write this the other way. Simplify our life. So the probability of A. So we assume this probability of A equals the conditional probability of A given B. And this is the probability of the intersection divided by the probability of B. And now, if we just multiply this by both sides, then we get exactly this condition, which implies independence. So that is independence. So we've proved this implication, we proved this implication, and that's our proof. So that's a nice proposition. It's another way to think about independence. But you should remember that this only applies when the probability of B is strictly positive. So let me give you another little proposition here. Actually, let me give you an example. We'll do an example. This is a nice example to illustrate these concepts. So let's take omega, our sample space, use our terminology, to be just the numbers from 1 to 4. Just a nice little space. And maybe I'll say in this case, wouldn't always say, but in this case we'll say that our sigma algebra is just the power set. And we're going to define our probability measure, P, to be uniform. So we'll just take P of k to be 1 over 4 for all k. Now let me define some sets. So we'll define our A. It's a different A. This is script A. This is just regular capital A. This is the event A. The event B will be 1 and 3. And the event C will be 2 and 3. 3. Now I've got a question for you. A few questions. See if you can solve these questions. So are A and B independent? What do you think? See if you can work it out. Are A, B, and C mutually independent? Are they pairwise independent? And here's a third question, are A and B independent, conditionally independent that is, given C? Sometimes people just say, are A and B independent given C? And when you say given something, you're implying that you mean conditional independence. So here's 3 questions for you. A nice simple example, and I would encourage you to work this out and see what happens. See if you can answer these questions. They're pretty easy to work out in this very simple case. Let me give you... Actually, let's stop there, and next time we'll pick up with some more very useful properties of conditional independence that come up a lot in statistics and machine learning and a lot of other fields too. So we'll be back soon with more conditional independence.